Hello, everybody, and welcome to our class today, 2D lines to 3D pipe networks for mega projects, but also small projects. A little bit about myself. My name is Jeff Fry. I work with HDR. I've been a CAD and BIM manager for 30 plus years, been with HDR for 8 years. I'm currently the horizontal BIM lead for the Ontario Line project, and this will be my third year as an AU speaker. I brought with me today two colleagues. I'll first introduce Cameron Schaefer.
Thank you, Jeff. So I'm Cameron Schaefer. I'm with HDR and I'm our transportation data acquisition lead. I'm also the digital design lead for the Ontario Line TA project. And I'm a professional engineer with a design background of just over 10 years of highway, roadway, drainage and transit design. And this will be my second AU as a speaker.
Thank you, Cameron. I also brought with me Sean Hulbert.
Thank you, Jeff. My name is Sean Hulbert. I am also a civil engineer in the state of Oregon. I have 30 plus years in design experience leveraging Autodesk software. I have been an advocate for BIM for civil infrastructure for quite some time now, and I've been an AU speaker since 2011.
Great, thank you, Sean. A quick agenda, we'll give a project overview. We'll talk about the data that we had to contend with. We'll talk about the relationship between HDR and Autodesk. We'll talk about the possible workflows. We'll talk about the actual workflow that we employed. And then we'll close it out with all of that data in action. So a quick project overview. I've asked Cameron to give us a high-level overview of all of the project data that we had to deal with today. Cameron?
Great, thank you, Jeff. So yeah, let's jump right into the Ontario Line project. This is a 16-kilometer freestanding subway line. We've got tunnels, portals, elevated guideways and bridges, 15 stations, site civil packages, roadway and utility packages. This is a $11 billion construction value, and this is expected to accommodate just over 400,000 daily boardings once complete. When we look at the digital delivery platforms, we're using 5 primary design software platforms. And in my role as the digital design lead, it's critical that this data must be viewable on all platforms and while maintaining the metadata and its associated attributes. When we look at our team, we're comprised of just over 300 model element authors with various skill sets, product knowledge, and expectations. So jumping right into the Ontario Line project, we're utilizing the models and the modeled content that we develop on this project across the board for 3D clash detection and comprehensive issue management. We're taking those same models and using those to support our 4D phasing efforts. And then lastly, we're taking all of that modeled content and dynamically bringing that into a comprehensive GIS portal, both in the 2D and 3D perspective. We're going to talk quite a bit about some of the different software platforms that we use and how we use them. But between Revit, Civil 3D, InfraWorks, going all the way to Navisworks and BIM 360, it's critical that we share this information fluidly. And when we look at the overall scope of the number of models on this project, we're projecting them to be just over 250. So when we started this project, kind of one of the first tasks we looked at was, what do we need to get to? What is that end result? And a well-defined BIM execution plan was absolutely critical to being able to define the roles, the BIM uses, and the expectation and coordination between our disciplines. We needed to ensure we were setting up protocols early and being flexible to adjust as needed. With this many people on a project, there's no such thing as too much communication. So over communicating is critical to getting the word out. We needed to understand our project needs and how these models intended to be used. And then from the very beginning, we needed to understand how we can leverage our existing data sources regardless of the platform that they reside. And one of the first things that we looked at on this project was the wealth of GIS information and existing utility data that was available to us, but not being properly utilized within the design environment. So from day one, I reached out to Jeff and I said, Jeff, we got to do more with this. What can we do with this 2D information, and how can we leverage this in our digital design environment? So I'll hand it off to Jeff for him to talk about the next steps.
So Cameron's right. He handed me a lot of data. I'll give you a little bit more background information on that. We had 3 file storage systems on this project that we're contending with, and that's BIM 360, ProjectWise, and SharePoint. The project itself was broken up into 5 fairly equal segments, mostly for file size reasons. We had 15 disciplines that needed to share this existing utility data in all of their own pieces of software. So I needed to have all of the data available in a Civil 3D format, Revit format, GIS, and ultimately be able to be exported to Navisworks. The actual data that I received was gridded off through downtown Toronto into a series of 150 individual XREF files. These individual XREF files, when combined, created the network of all of the existing utilities in the downtown core. As we get a little closer, we can see a typical intersection where we have a spaghetti mess of utilities that we were looking at. We decided on this particular project and workflow that we would model all of the existing utilities that we could make an assumed depth assumption about. For today's class, we'll be focusing on the 300 millimeter water main. So again, this is the big picture. This is what we received from our client and the city of Toronto. This is what we wanted it to look like. We wanted a 3D model, but we didn't quite know how to get here. We knew exactly what we wanted. We knew exactly what we had, but we were missing some steps. There's several ways we could have looked at this, but we decided, Cameron and I, to reach out to Sean at Autodesk. And I'm going to hand it over to Sean for a couple minutes, and he can talk about his process he went through for his workflow.
Thank you very much, Jeff. So it was perfect timing that Jeff requested Autodesk assistance for this process. I had just returned from the ASCE Construction Institute conference weeks before, where existing underground utility modeling was a very hot topic. We started by evaluating the need to model existing utilities in 3D, since we were introducing disruption to the existing process. We also have to have the answers to the questions that will be asked. So what are the benefits of modeling existing utilities in 3D? Well, you gain better coordination and confirmation with the utility owners, advanced scheduling of relocations and disruptions, improving communication with the public, and going forward, to quote the project manager for the regional connector project in LA, all urban infrastructure projects are utility relocation projects with an infrastructure element. So we also have to talk about the deltas when we're considering modeling existing utilities in 3D. Many of the utilities are unknown locations, and we're making a best guess at most. There's an additional cost and time associated to the project. And then there were challenges with some of the known workflows. This is where HDR and Autodesk partnership excelled. Next, we'll talk about the decision-making process. Empowering decision makers is an internal initiative here at Autodesk to help identify stakeholders during the decision-making processes. The important part is to understand the level of impact and influence each stakeholder has regarding the specific decisions. The decision to model existing utilities in 3D will impact the entire design team, and the team will have some level of influence over the decision. As we look at our stakeholders, we'll see that the construction and design team has some impact, but very low, also a low influence over the decision. Now, our client and utility owners will have more impact, however, the influence, however, the impact won't be as high. The designers, surveyors, and project engineers will have a greater impact, but also a lower influence on the decision. Now, our BIM coordinator, CAD manager, and project managers are the individuals who have the most impact, as well as the most influence over this decision. So Jeff and I chatted about the known workflows to evaluate the options. Again, we need to consider why we're modeling the existing utilities in 3D as we talk about these workflows. We looked at using 2D line work, However, the 2D line work provides little to no value in the model. We also looked at using AutoCAD solids, but the deltas here are that it's difficult to create these solids as well as a manual process to add elevations. We considered leveraging feature lines to represent utilities, but the feature lines we're forced to manually add each crossing to our profiles, or the networks become individual per feature line. So we decided on a hybrid approach using Civil 3D and a GIS workflow to create our existing utility model. Jeff is going to walk us through the steps that we used.
Great, thank you, Sean. So all of that information that we received from Sean, we took, and I tend to be a nuts and bolts guy. And so I needed to look at employing existing AutoCAD commands, Civil 3D commands, Civil 3D objects, AutoCAD objects. I needed to figure out all the nuts and bolts on how to make that happen. So we came up with 6 easy steps for anyone to follow on this. So I'll talk about these 6 easy steps. The first 2 steps, isolating the objects in your drawing, using simple AutoCAD commands to freeze or detach XREFs, getting it down to just the data that you want to model. That helps with file speed, that helps with your accuracy, that also helps simplify your models. The next is to assign elevations. We'll take these lines and we'll turn them into feature lines. We'll drape them on the surface, representing our 300 millimeter water line. It's about a 12-inch water line. We will be moving those lines 1.8 meters, roughly 6 feet below existing ground. And then we'll ultimately explode those down to their most native object, and that is a 3D line. Then we'll set some values to those objects. As 3D lines, we'll double check their layer. We'll use an elevation 1 and an elevation 2 to represent the start and end elevation for the pipes. In our case here, we're going to be using the crown of the pipe, and we'll set thickness of those objects. By setting the thickness, you'll note in the videos coming up, I set that thickness to 300 millimeters. That 300 millimeter thickness is then used to identify the pipe size in our network. We'll export that to a shapefile using the map export command. And the last 2 steps, we'll create a parts list for our custom part, and we'll import that shapefile as a pipe network and put it to use. So I'll start off here demonstrating our background information that we had to deal with on this project. We had a very extensive topography. Again, we're isolating our objects, so I'm going to go ahead and right-click and we'll detach that. In this drawing, I also have all of these other utilities for this particular stretch of road. For the sake of this class, I've already bound the information for our 300 millimeter water line. As you'll see, that's the water's XREF is isolated in this file. We'll zoom up over here just to demonstrate the command called lay ISO. I'll start by isolating the 300 millimeter water main, our 2 track lines, and a random rectangular boundary that I've selected. For the sake of this class, I decided to isolate our objects down to just this small 1.5 block area. There's another command that I like to use, and it's called map trim. Map trim gives us a dialog box, allows us to select a boundary. I'll go ahead and select the boundary in our drawing, just showing that this area of inclusion is really, really big, but I want to focus on just this area. The regular trim command in AutoCAD isn't quite as powerful. I want to select manually the objects I want to trim. I'll zoom out and I'll grab everything, hit enter. And this brings us to the final step in this dialog where I can trim outside the boundary. I'll skip topology objects, and I don't need to retain the object data. This just says that it will not be performed on frozen or locked layers. So this is isolating our data, only that data that I want to continue modeling with. In the next step, we're going to assign elevations. The very first step in assigning elevations is to make them into feature lines and drop them on the surface at a lowered elevation. Just want to note in here in this drawing, it could be lines, could be arcs, could be polylines. These happen to be lightweight polylines. Notice the layer is waterline active TUGS. And also notice that the Z elevation is set to 0. And that's typical for all of these polylines in this drawing. Everything is set to 0. So we'll go up to the grading pull down and we'll choose create feature lines from objects. And we'll select all of these polylines in this drawing. We'll turn them into feature lines. Feature lines have an added complexity and a lot of intelligence. We can stylize them, but remember we're going to be exploding them, so styles don't matter at this point. I want to use the selected entity layer, right? Waterline active TUGS. I want to use that as a value layer. I want to go ahead and erase the existing objects. I want to assign elevations, and I want to not weed points because I want elevations at every vertice along the polyline. When I say OK to this dialog box, you'll notice here I have a surface OG2, that stands for original ground 2. That's the second segment in this project. Notice that I have insert intermediate grade breakpoints turned on. That will create a new pipe every time that polyline crosses a tin line, as well as every vertice in the polyline. So OG2, our relative elevation to surface was minus 1.8 meters. Again, roughly 6 feet. And we'll say OK to that. Now we'll take a look at the feature line itself, just to show that it has value. You notice the grips change to feature line grips. Right click, we'll go to elevation editor. And we'll look at some of the values here. Just notice that now there's elevation set. And in the second column, you'll notice it's 1.8 meters below existing ground. So as I mentioned earlier, we have to explode these objects down to their most basic object, and that is a 3D line. So we'll use the explode command. We'll explode them once. The first explode of a feature line makes them a 3D polyline. We'll go ahead and use the explode command again and take them down to that basic object of 3D line. And we'll take a look at the properties of a 3D line. Notice it maintained its layer. It has a Z elevation, 83.46, 83.48. So we'll come back to the drawing, and now we have our elevations assigned. We don't have our thicknesses yet, so we need a couple more properties set before we start making our pipe network. So here again, we have our 3D line. You'll notice it's a line. You'll notice it has a layer, waterline active TUGS. Down here, it has a start Z, and it has an end Z. So that would be Z1 and Z2, and its thickness is set to 0. In our class, we've decided that we want to model our 300 millimeter waterline. So I'm going to set all of these objects to a thickness of 300 millimeters. Simply selecting all of the objects in our drawing, using basic AutoCAD and Civil 3D selection tools. I've selected all the objects, and now I can go to the Properties dialog box, and I can set the thickness of all of those at one time to 300 millimeters. You don't have to type millimeters because that's the units in our drawing, so I can leave that off. So now all of the highlighted lines, 3D lines, are set to a thickness of 300. And we'll show that in the dialog box. They're all set to 300. They have a start Z elevation and an end Z elevation. Again, we'll be using that as the crown of our assumed depth utilities. And it has a layer property set of waterline active TUGS. So the next step is to actually export this out to a shapefile. So we'll do that in this step here. We'll use a command called map export. Map export gives us the ability to name a shapefile. I like to name these shapefiles the same name that I will ultimately name my pipe network. So in this case, I'm saying existing 300 millimeter water. That's completely customizable by the user. The object type that I want to export will be line type. And I don't want to select all, I want to select manual. And again, I'll select all these objects in my drawing. So everything is highlighted, everything is selected. The next thing is the data that I want to attach. We do that by hitting select attributes. We'll look at the attributes that are selectable. We'll come down and grab layer. Remember, waterline active TUG. The next attribute we'll grab is thickness, 300 millimeters. And we'll grab Z1 and Z2. Note that there are a lot of attributes available to us in this dialog box that could be written out as well and make your model even more powerful. Those 4 basic attributes that we selected gave us the most powerful model for our needs at this time for our assumed depth utilities: layer, thickness, elevation 1, elevation 2. So we'll take that data and write that out to a shapefile. The benefit of this shapefile, it can be used in GIS. We plan on actually bringing it back into Civil 3D, but that data could be used in a GIS environment, ultimately fulfilling one of the needs that Cameron had with his interoperability for this data. In any pipe network, an important part is to have a parts list. So for the sake of this class, I'm going to cover the basics of creating a part list. There are other classes available at AU for that task. I'll clear the screen. I'll go to the pipes pull down, parts list, and I want to create a brand new one. I don't have an existing one. I want to go ahead and make a brand new parts list, and we'll call that existing waterline. We are only modeling pipes in this scenario, so I want to right click and add part family. I'll select the top one, concrete pipe, basically because those are circular pipes and all the pipes I want to model are circular. Under concrete pipe, I need to add a part size. So in this case, the part size I want to add is 300 millimeter. And I'll just double check that the units are set to millimeters, and I'll say okay. Now, the description on this pipe is 300 millimeter concrete pipe, but I don't want that. I want to change that to existing water. It's currently stylized as a double line storm. Since this is a canned presentation, I already have a double line water style set up. Again, there are other classes available through AU for creating and editing your existing styles. So we'll set this to double line water, and we'll say okay. Now we've stylized a brand new pipe that we created called 300 millimeter existing water. And just to show how easy it is to actually create pipes, I've gone through and we'll edit the existing water parts list. And I'll go ahead and add another pipe size in here just to show that you can add multiple. So we'll right click, add part size. This exercise will go through and just create a 400 millimeter existing water line. We'll change its style and its description to match the 300 millimeter existing water line. Here we'll just click the double line water, and you could flesh that out with all of your different custom sizes. Now that we have our parts list created, we have our shape file. Now the next step and the last step in this process of creating 3D networks from 2D lines is to actually import that shapefile as a pipe network. So we'll go to the Insert tab in our ribbon, we'll go to the Import, and we'll import GIS data. We'll browse out on our C drive or on our network drive to our shapefile that we created. We'll hit the Connect button to connect the data to our current drawing. And through the wizard, we can name the pipe network. So we'll say existing 300 millimeter water. Our parts list is our existing water parts list. And we don't have a surface alignment or structure labels or pipe labels. At this point, we're not going to be labeling them. We'll take the default schema. Now in this window, remember I said we had circular pipes. I'm going to add that to our list. AutoCAD automatically assigns wall thickness to thickness. So I want to strip that out really quick. And we'll scroll up here, and the description for all of these pipes, I want to be the layer that those pipes existed on before. Remember, waterline active TUGS. The second thing we would set in here would be the start crown elevation. We'll set that to value Z1. End crown elevation we'll set to Z2. And we'll scroll all the way to the bottom, and we will add the thickness as the inner diameter. And this is a must. You have to set the value here to millimeters, or you will get the incorrect pipe size coming from your part list. So to recap, we have the thickness set. We have Z1 and Z2. And we have the layer set as our description. Well, next, we don't have any structures in this particular workflow. I want to import all of the GIS data that I just modeled, but you could use some of the query tools to pare that selection down. We'll hit next and ultimately finish. Takes a few minutes. For the sake of this class, I've sped some things up. And hopefully we get to a point where your GIS data was successfully imported. Here's the start of our 3D model. We'll take a look at it in a 3D orbit command in just a second. The first thing we're going to do is look at the pipe properties. So just to verify, we have a pipe. It has a description of waterline active TUGS. So that description now flows through all of those pipes. The style was set correctly. We'll look at the part properties very quickly and notice that it is set to 300 millimeter concrete pipe. If you want to add a little more value to your model, you can come down to the material field and you can change reinforced concrete to PVC if you wanted to. Now we've added additional value that didn't exist before. And you'll notice that it has elevations. So it's not at elevation 0 anymore. We've ultimately created a 3D model now. So now we'll look at this in 3D. And you'll see that we have a fully fleshed out 3D model, assumed depth of 1.8 meters below existing ground of a 300 millimeter water line. This could be 1 block long. This could be several miles long. All of the same steps would be employed on your project. So that closes out that piece. With any workflow, there are some known issues. There are some possible solutions that we could look at. I want to talk about 4 known workflow issues that we had. One was file size. Our file size was very large. If you remember, we have a pipe at every polyline vertice and every break in every triangle in the tin. Assumed depth utilities will conflict. If you remember from our 3D orbit a second ago, all of those pipes were set to the same depth of 1.8 meters below existing ground. We know that pipes that cross the road, they go above and below each other. Those individual conflicts would need to be resolved in the field with a pothole or other as-built information. But since you have a pipe network, you can do that. We just opted to push that conflict analysis down the road, as it wasn't as important for us for these existing utilities. We're draped on the surface. So if your surface changes, these pipes automatically won't change. So that's something to keep in mind as well. You would have to remodel these things as you get additional information on your from your surface. It also created a pipe at every single DTM triangle. I can't emphasize that enough. If you omit that, you lose a little bit of accuracy, but your model will be quite a bit smaller. And the last thing that I want to talk about, and Sean mentioned it earlier, we could have used feature lines. Feature lines are a very acceptable use case for 3D utilities in this linear arrangement. But since we had so many consumers of this data, we had GIS, we had Revit, and we had Civil 3D users, it was very important that this data be broken down to the least common denominator, which was a Civil 3D pipe network. When I wrapped all of this up and we presented it back to Sean, and I said, here we are, Sean, we're very proud of what we've come up with. I said, what would we do in the future? So I'm going to let Sean talk about some potential improvements to process.
Thank you again, Jeff. And so what next, you ask? Well, by leveraging Civil 3D again, the ArcGIS connector for Autodesk ArcGIS connector and Dynamo, we can expect to increase our overall efficiencies. We can improve our model accuracy. We can introduce automation to our process, and we can allow for faster consumption of the data, just to mention a few. So let's go ahead and hear how the data that we put together was used.
Thank you, Sean. So I'm going to talk a little bit about this wealth of information that we now had from the utility standpoint from Jeff, and this very rich 3D model. And what do we do with it? So let's jump a little bit into a technology focus and looking at our digital design strategy. The first area that we utilize these models Jeff created, and you can see them in the fly through to the right here, is within our federated model. This is our weekly project model that takes all of our different disciplines and puts together the snapshot in time of how we are progressing with our design. This is updated weekly and available for download on BIM 360, and it contains our source models for plan production. This is the framework of the existing conditions that are used for clash detection, 4D phasing, and also used to visualize in conjunction with our reality mesh and LiDAR project data. Another way we utilize this information is in our model tracking dashboards. So you're seeing a screenshot here of one of the dashboards that we use to keep track of our segments, our disciplines, our model element authors, and understand how these models are progressing, if they're set up correctly, and to keep track of how many models we have total in this project. This is used as an up-to-date source of truth for model progress and QC during our design, and it allows us to look at models like the ones Jeff has and keep quick dashboard tracking stats on those to share with the team. Our next area is our 3D cloud-based clash detection. So what you're seeing here is one of those existing utilities models, and being able to take that content and automatically clash it against proposed design content. This is going to tie into our issue management for clashes that are assigned to our individual model element authors. And we also have the ability to tie these clashes into custom Power BI dashboards and report and trend our clashes over time. And then our last case is our 4D construction phasing. Being that the existing utilities are such a critical component of any project and how something is going to be phased, this is just a sample of how we take that information that Jeff had produced and how we can tie that into work breakdown structure codes from P6 to schedule dynamically used models tied to our scheduling information. And as these design models change over time, or the WBS codes are maintained or updated, we're able to take weekly kind of snapshots and simulation updates to report on new processes. This construction phasing and logic is also being integrated into our dynamic 2D GIS dashboard. So as we're kind of looking forward, similar to what Sean was talking about, and we look at better ways to leverage information across projects and share design amongst better stakeholders. Opening up the connectors and the platforms between Esri and Autodesk really just allows better BIM through GIS data. We can utilize our surfaces for assumed depths, allowing clash detection to automatically highlight areas of potential concern, and the ability to normalize data between different applications fundamentally increases our design efficiency and reduces our project risk. So with that, I'm going to hand it over to Jeff to summarize what we've reviewed today.
Thank you, Cameron. Thank you, Sean. So what did we do again? Let's talk about the 6 steps one at a time, and maybe again, a high overview. We isolated the objects. The reason I did that is I'm a CAD professional that believes that a clean workspace is a simple workspace. We assigned elevations to those objects. So we created feature lines, we draped them on the surface, we exploded them down to their basic elements, and we assigned a thickness value to those. When we set the properties, we used the existing layer. So that was a layer provided to us by the client or by the jurisdiction or the municipality that gave you the data. We used the Z1 and Z2 that was provided to us by the surface. And we set that thickness that I've mentioned. We used the map export command, and we created a shapefile that was then usable in GIS for several applications that Cameron mentioned. We ultimately imported it back in to our AutoCAD environment. We created a custom part list. We used out-of-the-box sizes, granted, but you can customize those. Again, there are classes available through Autodesk on that. And we imported that back as a shapefile, or imported that shapefile back in as a pipe network. That's where the power begins. That's where you have ultimate access to that data and can customize it just like any one of your design XREFs. There is a handout available, step-by-step instructions with some screen captures on how to do this, also available in the link here at Autodesk University. So with that, I thank everybody for coming.